Laplace transforms, let me tell you the importance of Laplace transforms in for various branches like electronics and communication, electrical and electronics, instrumentation engineering, like these branches. So that is electrical sciences branches. So Laplace transforms is very prerequisite for many core subjects like control systems, signal systems, like this. And even this subject is very useful for other branches like mechanical, civil, chemical engineering, like this, right? So in this session, we discuss the basic concepts of Laplace transform, definition of Laplace transforms, various properties like linear properties, shifting properties, change of scale properties, etc., convolution products, and then followed by few examples, right? Now, let us start the session with definition of a Laplace transform. Suppose we have a function small f in the variable t. We have a function f in the variable t. Now, basically this t is a time variable. So its Laplace transform of this function is denoted by L of f of t. This is also denoted by capital F of s. So small f is original function, its Laplace is capital F, and this s is a signal variable. S is a signal variable, t is a time variable. So therefore Laplace of small f of t is denoted by L of f of t, that is also denoted by capital F of s. And this is nothing but the integral 0 to infinity e power minus st into f of t dt, provided this integral exists. Provided the integral exists. Here integral exists means it's a valid finite number. So basically it is a function in terms of x. So this is f of t, a function in the variable t, time. So its Laplace is denoted by L of f of t, which is given by capital F of s. So this one is one representation, this is another representation. Small f is a function in the variable t. When you discuss its Laplace transform, we get capital F. Always remember that small f is original function, capital F is its Laplace transform, and the result we get in terms of s. This is time variable and this is signal variable. So therefore this is nothing but integral 0 to infinity e power minus st into f of t dt, provided this integral exists. Now let us discuss one example. Suppose let us find L of 1, that is f of t is 1. So according to this is integral 0 to infinity e power minus st into 1 dt, because my function is 1. Now this is nothing but e power minus st divided by minus s. We are integrating this function with respect to time variable and apply the limits. So therefore here this is minus 1 by s into e power minus s into infinity. This is e power minus infinity minus e power minus 0. This is minus 1 by s into 1 by e power infinity. E power 0 is 1. E power infinity is infinity, 1 by infinity is 0. So therefore this is minus 1 by s into 0 minus 1, and the result is 1 by s. Therefore the conclusion is Laplace of 1 is 1 by s. Now this is the basic definition of Laplace transform, followed by an example, right? Let us write this point. Let f of t be any function. Let f of t be any function in the variable t. Let f of t be any function in the variable t. The Laplace transform of f of t, the Laplace of f of t is denoted and defined as, the Laplace of f of t is denoted and defined as L of f of t equal to capital F of s equal to this. L of f of t equal to capital F of s equal to integral 0 to infinity e power minus st into f of t dt, provided the integral exists. Integral 0 to infinity e power minus st into f of t dt, provided the integral exists, where t is a time variable and s is a signal variable. T is a time variable and s is a signal variable. Write this example. Now based on this definition, let us give few formulae of Laplace transform of few basic functions, very standard functions. So the first formula is Laplace of a into f of t plus or minus b into z of t. Here we have two functions, f of t and g of t. A and b are constants. Between these combination, we can have either plus or minus. And this is nothing but a times L of f of t plus or minus b times Laplace of g of t for all constants a comma b. And this property we call it as linear property. Here Laplace is nothing but an integral. So integral follows linear properties with respect to either plus or minus. So this is one important property. And let us discuss Laplace of some more formulae. Laplace of e power at, exponential function. This is nothing but 1 divided by s minus a. A is some constant. Just now we got Laplace of 1. This one we can write it as L of e power 0 t. E power 0 is 1. So what is a? A is 0. So therefore you can replace a by 0. We can get it 1 by s. Just now we proved that Laplace of 1 is 1 by x. In fact, this is the extension of this formula. So in place of e power at, replace a by 0. We get Laplace of 1 as 1 by s. Third one is Laplace of sine function, sine at. A is a constant and this is given by a divided by s square plus a square. Next one, Laplace of cos function. So this is nothing but s divided by s square plus a square. For both third and fourth formulae, the denominator is same, s square plus a square. In case of cos, variable will come as a numerator part. In case of sine, constant will come a. Now next one is Laplace of t power n. This is where n is some constant. This is nothing but gamma of n plus 1 divided by s power n plus 1. But we know that gamma of n plus 1 is n factorial. So this is again n factorial divided by s power n plus 1. See, if n is a positive integer, you can apply directly this formula. If n is a fraction like 1 by 2, 3 by 2 like this, we know how to get the values of gamma 1 by 2, 3 by 2, that is multiples of 1 by 2. Then you can proceed this because factorial may not be possible for fractional values, right? So Laplace of t power n is gamma of n plus 1 by s power n plus 1. You always apply this formula for any constant n. In particular, if n is a positive integer, directly you can write n factorial divided by s power n plus 1. Now based on these examples, these properties, let us discuss one or two examples. Suppose I want Laplace transform of, for example, t square minus sine 3t. Now this is f of t, this is g of t, constants we have 1. In between functions we have minus symbol. So this is nothing but Laplace of t square minus Laplace of sine 3t. Now this is a positive integer. Apply formula number 5. This is n value is 2. 2 factorial. So 2 factorial divided by s power 2 plus 1. This is 3. A value 3. So 3 by s square plus 9. So therefore this is 2 divided by s cube minus 3 divided by s square plus 9. Now let us discuss one more example. Suppose I want Laplace of 1 by square root of t. Laplace of 1 by square root of t. Now this can be written as Laplace of t power minus 1 by 2. Now again we need to apply formula number 5, but in that case the value of n is fraction value. It's not a positive integer. So let us express this Laplace in terms of gamma function. So here this is gamma of minus 1 by 2 plus 1 divided by s power minus 1 by 2 plus 1. So this is gamma of 1 by 2 divided by s power 1 by 2. We know that gamma of 1 by 2 is root pi. So root pi divided by root s. So therefore the value is root pi divided by root s. So Laplace of 1 by square root of t is square root of pi divided by s. So you write basic formula followed by example 1 and example 2. Next concept is shifting property. Let us see what it is. Suppose if Laplace of small f of t equal to capital F of s, then the Laplace transform of e power at into f of t is nothing but capital F of s minus a. This is called shifting property. So what does it mean is, if I know the Laplace of small f as capital F, then using this Laplace transform I can easily get the Laplace of e power at into f of t. Just to replace s by s minus a. This a is important constant. So just we know the Laplace of small f of t as capital F of s. So if Laplace of small f is capital F of s, using this Laplace I can express Laplace of e power at into f of t again in terms of f, but s is replaced by s minus a. Suppose that means s is shifted to s minus a. So that means when you consider x-axis, for example like this s-axis, now if a is positive, it will be relocated to left side. If a is for example negative value, it will be shifted towards right side like this. So either this or this. Therefore, if a is positive, it shifts towards right side. If a is negative, it shifts towards right side. If a is 0, it will be in the same position. So it may shift to either right side or left side, depends on the value of a, whether it is positive or negative. That's why it is called a shifting property. Let us see an example. Suppose I want to know Laplace transform of e power 2t into cos 3t. I should know Laplace of e power 2t into cos 3t. So assume that f of t equal to cos 3t. So to get the Laplace of this, at first I will find the Laplace of cos 3t. So its Laplace transform is capital F of s. This is s divided by s square plus 3 square. This is 9. Now this is the Laplace of only cos 3t. But I should know Laplace of this. Therefore, this Laplace of e power 2t into cos 3t, this is nothing but f of s minus 2. Here the value of a is 2. When you are finding Laplace of cos 3t, a is 3. When you are finding Laplace of e power 2t into cos 3t, a becomes 2. So therefore, this is f of s minus 2. This is f of s. So replace s by s minus 2. So therefore, this becomes s minus 2 divided by s minus 2 whole square plus 9. Right? So note this point followed by this example. S property, change of scale property. Suppose if Laplace of small f is capital F of s, if Laplace of small f is capital F of s, then Laplace transform of f of at, where a is some non-zero constant. This is given by 1 by a into f of s by a, where a is a non-zero constant. Because a is written in the denominator, it should not be 0. So I will tell you why it is called change of scale. Suppose when you are working with scale properties, right, sometimes you may work with the unit scale. Unit scale. That means so scale will be like this. This is 1 unit, 2 units. 3 units, this is 0, here it is -1, so -2 like this. The distance between consecutive 2 points is 1, so it is a 1 unit scale. Suppose if you ask me what is a 2 unit scale, so maintain the gap of 2. So that means I maintain 0, this is 2, 4, -2, -4 like this. So here this original scale is T, but T is multiplied with A. This is a T scale and this is AT scale. Just like if T equal to 1, this is unit scale. If T equal to 2, this is a 2 unit scale. Therefore, this is scale of A, this is scale AT. So therefore, if Laplace of small f of t is capital F of s, then Laplace of f of small at equal to 1 by a into f of s by a, where a is not equal to 0. So that means once I get the Laplace of small f, I can easily get Laplace of f of at in terms of again capital F. But s should be replaced by s by a. Let us take an example. Suppose we want Laplace of, for example, I should know Laplace of cos 2t. I want Laplace of cos 2t. Then in that case, what I will do is, here a value is 2. So I can take g of t equal to cos t. So the Laplace transform is denoted by g of s. This is nothing but s by s square plus a square. Here a value is 1. S by s square plus 1. I want Laplace of cos 2t. But here a value is 2, so you need to apply this. But before applying this, take g of t equal to cos t. So its Laplace is capital G, that is given by s square plus a square, because here a value is 1. But when you come to this, a value becomes 2. So please try to understand this. Here a value is 1 and this is a value 2. But I want Laplace of this f of t. So this is nothing but Laplace of cos 2t. So this is nothing but Laplace of, if g of t is cos t, then cos 2t is nothing but g of 2t. So Laplace of g of 2t. Now you can apply this. This is nothing but 1 by a. 1 by a into g of s by a. Here a value is 2. So therefore this is 1 by 2 into, replace s by 2. So s by 2 divided by s by 2 whole square plus 1. So you can simplify this. You will get s by s square plus 4. We know that Laplace of cos 2 is s by s square plus 4. Just to get the result by using change of scale property, I found like this. So f of t is cos 2t. So g of t is cos t. Because this is cos at, f of at. So take g of t equal to cos t. Find its Laplace transform. Here a value is 1. This is s by s square plus a square. So therefore, but I want Laplace of f of t. This is nothing but Laplace of cos 2t. So if cos t is g of t, then cos 2t is g of 2t. Therefore, Laplace of g of at. You can apply this formula. This is 1 by 2 into g of s by 2. Simplify this. You will get s by s square plus a square. Note these points followed by this example. Next one is multiplication by t power n. Multiplication by t power n. Suppose I know that Laplace of small f is capital F of s. Now using this Laplace, we can easily get Laplace transform of t power n into f of t. That's why it is named as multiplication by t power n. And the Laplace of this new combination gives -1 whole power n into dn by ds power n of f of s, where n equal to 0, 1, 2, 3, etc. like this. So here n values are integer values along with 0. They will be called as whole numbers. So you can take n value 0, t power 0 is 1. Then its Laplace becomes -1 whole power 0, 1. D power 0 by ds power 0, that is 0th derivative. Again you will get the same function. So this is very useful when you take n value 1, 2, 3, etc. When n is 0, it is a trivial case. So when you take n value 1, 2, 3, etc., it works very perfectly. So once you get the Laplace of small f as capital F, you can easily get the Laplace of t power n into f of t again in terms of capital F of s. So this is a function in the variable s. Differentiate this with respect to s n times. Differentiate this with respect to s n times and multiply with minus 1 whole power n. Let us see an example. Suppose I want Laplace of t sin t. So this is in the form Laplace of t power 1 into sin t. So here n value is 1. So take f of t equal to this sin t. So to get the Laplace of this function, let us get the Laplace of this f of t sin t at first. Therefore, its Laplace transform is f of s equal to here a value 1. So a by s square plus a square. This is 1 by s square plus 1. Now, I can easily get the Laplace of this one using this property. Therefore, Laplace of t power 1 into sin t equal to, according to this formula, n value is 1. So, this is minus 1 whole power 1 into d by ds of this f of s. This is 1 divided by s square plus 1. This is minus 1 into, you assume that this is s. D by ds of 1 by s minus 1 by s square. So therefore this is minus 1 by s square means s square plus 1 whole square into the derivative of s square plus 1 is 2s. Therefore the value is finally 2s divided by s square plus 1 whole square. Like this you can get the Laplace of t square of sin t, t square of cos t, t power 4 of cos 2t like this. So note this point followed by this example. Next one is division by t. In the previous, we have seen Laplace transform of multiples of t power n. Now this is division by t. So if Laplace of small f is capital F of s, then Laplace transform of f of t by t. Laplace transform of f of t by t. That's why it is called division by t. This is nothing but integral s to infinity capital F of s ds. So integrate this Laplace transform capital F of s with respect to x from s to infinity. So always we are getting the results in terms of capital F only. In the first case, the result is f of s minus a. In the second case, it is 1 by a into f of s by a, change of scale property. First one is shifting property. So we got the result in terms of capital F of s like this, f of s minus a. In case of change of scale property, it is 1 by a into f of s by a. In third case, that is multiplication by t power n, it becomes minus 1 whole power n into nth derivative of capital F of s. Now again, here we are integrating this function. In case of multiples of t power n, we go for derivative. In case of division by powers of t, we go for integrals. But whatever the result is, always the result is depending on Laplace of small f. That's the key point in this case. Now let us see an example. Suppose I want Laplace transform of sin t divided by t. So it is in the form Laplace of f of t by t. So my choice for f of t is sin t. Here a value is 1. So the Laplace transform of this one is 1 divided by s square plus 1. Therefore, Laplace of sin t by t. According to this formula, this is integral s to infinity 1 by s square plus 1 ds. So integral 1 by 1 plus s square ds is tan inverse s. Apply the limits from s to infinity. Tan inverse infinity is pi by 2 minus s is replaced by s. So the result is pi by 2 minus tan inverse, or you can write it as cot inverse s, because tan inverse s plus cot inverse s equal to pi by 2. Tan inverse s plus cot inverse s equal to pi by 2. Note this point followed by this example. Next one is Laplace transform of integrals. Suppose we have Laplace of small f of t equal to capital F of s. Then the Laplace transform of integral 0 to t f of t dt. So that's why it is called as Laplace transform of integrals. We know that Laplace transform of small f of t is capital F of s. In that case, the Laplace of integral 0 to t f of t dt. This is given by 1 by s into f of s. So answer is expressed in terms of f of s. The Laplace transform of small f is capital F. In that case, the Laplace transform of integral 0 to t f of t dt is 1 by s into f of s. Now we discuss Laplace transform of derivatives also. This is very important. Using this point, we can easily solve higher order linear differential equations with the constant coefficients. So first let me tell you the formula for this. Suppose if Laplace transform of small f of t equal to capital F of s, then the Laplace transform of nth derivative of f with respect to t. So here n is written in parenthesis. That means it represents nth order derivative of f of t. So I know the Laplace transform of f of small f as capital F of s. Then Laplace transform of nth derivative of f of t, its Laplace transform again depends on this capital F. This will be given like this. This is s power n into capital F of s minus s power n minus 1 into f of 0 minus s power n minus 2 into f dash of 0 minus s power n minus 3 into f double dash 0 minus and so on minus n minus 1 the derivative of f at 0. This is the value. See, in this expression only the first term will have plus sign. In the rest of the cases the sign is minus only, minus till the end of last term. So even in the first term only we are using capital F, its Laplace transform. As you are moving from left to right, the powers of s are in decreasing order. Here the power of s is n. So this is nth derivative. That means you can discuss first order derivative, Laplace of second derivative, Laplace of third order derivative like this. So n is a positive integer. So here it is n, n minus 1, n minus 2 and so on. Sorry, this value is, this is exactly, here the values of derivatives are in increasing order. That is exactly n minus 1 the derivative of f at 0. So here this is actually 0th derivative. This is first derivative. Next one you will get second derivative, third derivative and so on, n minus 1 derivative. So as you move from left to right, the powers of s are in decreasing order and derivatives are in increasing order. This is 0th derivative, first derivative, second derivative. Like this you will go up to n minus 1 derivative. So this is f of 0, f dash of 0, second derivative of small f at 0, third derivative of f at 0 and so on, n minus 1 the derivative of f at 0. Only in the first term we are using its Laplace transform. From second term onwards we are using f of 0, f dash of 0, f double dash 0 and so on up to n minus 1 derivative 0. Suppose in this case if n equal to 1, this equation becomes Laplace of f dash of t. So that means n is replaced by 1. So we are finding Laplace of first order derivative of f. This is given by s into f of s minus f of 0. This is one useful result. Suppose if n is 2, implies we are discussing Laplace transform of second derivative of f. This is given by s square into f of s minus replace n by 2. This is s into f of 0 minus this one is f dash of 0. So this is the value of Laplace transform of second derivative of f with respect to t. So note these points and these points. Now let me tell you the importance of Laplace transform of derivatives. During chapter 2, we had gone through solving linear differential equations with the constant coefficients. If I solve second order linear equation with the constant coefficients, I need to supply two boundary conditions to get C1 and C2. Here when you look at the previous formula, f of 0 is required, f dash of 0 is required. If it is a second order equation, f of 0 and f dash of 0 is required. If it is a third order linear equation with the constant coefficients, it requires f of 0, f dash of 0, f double dash of 0. So using that formula and using inverse Laplace transforms, maybe we discuss in future sessions, we can easily solve higher order linear equations with the constant coefficients using the previous formula, what we seen in this session. Okay. So we continue the session in the next. So thank you so much.